That's right. All right, I think we can get started here. It's 1 o'clock on my watch. Welcome everybody. My name is Suresh Srinivasan. I coordinate the beginner special interest group for the MAS. Thank you guys for tuning in today. We have a really cool presentation by Steve Emert coming up in a second. Hi, RIC that you're on today too. So a little bit about the beginner group. Once a month we have events. During the winter we do presentations. Normally we do them in libraries, but in this COVID world, we're doing them virtually through Zoom. And this presentation is also being recorded, so keep that in mind. Let's see, normally we do presentations in the wintertime. So this will be the last one for this cycle. And then we start going back outside. Our next beginner group event is coming up actually next week, next Saturday, if the weather is good. We will be back at Metcalf Field, which is out near Afton. And we'll have telescopes set up. And then we also invite people to bring their own telescopes. If you've got one sitting in a closet somewhere that hasn't seen the light of day and you want to get it out, bring it, and we can help you get it set up and show you how to use it and help you point it at really cool things. So we'll be starting out there about 7 o'clock. Due to COVID rules, we're limited to the first 50 people, and we've already passed, I think we're almost about halfway there right now. So if you're interested, either drop me an email or just let me know. And if you want to put it on the chat here, I'll even write it down. But find me on the MAS forum or drop me an email at Suresh, SURESH, KS1 at MSN.com. I'll put it in the chat just in case anybody's looking for my email address. Our beginner observing events are a lot of fun. We're very laid back. We don't have a specific agenda on purpose because we want to be welcoming for people and not have them stress out over anything. We did post a list of 10 or 11 objects they can try for if they have telescopes or a pair of binoculars. So that's a new wrinkle that we're going to test out over the next few months. So again, if you have any questions about that, let me know. So now I'm going to introduce Steve Emert. Steve has been in the club for 20 years. He is on the Cherry Grove committee and does really, really good work down there, getting that facility up and running and keeping it running for us. It's a wonderful facility. So if you haven't been down to Cherry Grove and you're a member of the MAS, I recommend that you do that. Steve, did I miss anything, or is there anything you want me to add?
No, actually, probably more important is that for those that don't know, I'm the membership coordinator too, which doesn't really mean I coordinate much of anything, but it does mean that I maintain the membership database and send the welcome letters to new members and renewal letters to everybody else and all of that kind of stuff. So
Steve does one other thing that he forgot, and that is every once in a while, not every month, but every couple of months, Steve does a member orientation presentation, or I don't know what you even call it, Steve, where he'll walk you through the MAS, the various perks and talk about the facilities, talk a little about telescopes. Did I miss anything on that, Steve?
No, pretty much covers it. In pre-COVID days, I try to do that meeting in person at just as the BSIG meetings at one of the libraries around town in the meeting rooms. Unfortunately, COVID took over, so I kind of missed last year. But about a month ago, I did the orientation meeting online, and we've got that recorded and it's pasted up in the MAS announcement section, I believe, of the forum. So you can grab that. It's actually on YouTube, so you could search for Minnesota Astronomical Society on YouTube, as we're starting to upload all of these presentations up to YouTube as well. So you can go back and fast forward through that, because that one actually did make it 2 full hours, which was kind of, I'm not sure, surprising, something. Anyway. So anyway, go ahead and back through there, and yeah, we go through the leadership of the club. We go through what the sites are, what you do when you're doing star parties and that sort of thing, and what other benefits are available to members, stuff like that within the orientation.
So if you haven't attended one of those, I would strongly recommend you do. It's very informative. It's a good way of understanding what the MAS is all about. So today Steve's going to talk about astronomical terms or astronomy terms, and it's a topic that a lot of people think they know and don't always know all the different concepts and beginner kind of terminology or understanding that you have to have in astronomy. Steve said that he had listened in on a presentation. What was that, Steve?
Actually, I'll go to the second slide because that's my source here. Yeah, I listen to podcasts quite a bit. So if you're not aware, there's the 365 Days of Astronomy podcast that's been going on since the International Year of Astronomy, which was in 2009. So they've been doing this podcast for over a decade now. I happen to be listening to this one in January, and I'm going, wow. Suresh over this past winter has covered a lot of other fairly advanced topics for beginners, getting into imaging and stuff like that. So I'm going, it's been a while since we've just kind of gotten down to the basics of, what are these weird terms and, all these words that we've used that may be foreign to somebody that's just getting into the hobby. So I pulled up the information from that one and started building this slide deck and asked Suresh if I could present on it. And then as I was putting it together, I ran across this paper that I had that had a, A through Z listing of astronomical terms. And then while we were doing something else, Dave Faulkner said, hey, I can send you this listing I've got. And it turns out it was the same one. So I've got to give him credit for that one. But anyway, that's where the source of this stuff kind of came from.
Good deal. So there's one last thing for Steve starts off is we're using the chat feature here. So if you have a question, don't just verbally ask the question, put it into the chat. And then every few minutes I'll ask Steve the questions off the chat. It seems to make the presentations flow better and doesn't take the speaker off message. So if you got a question, just drop it in the chat. Now I'm going to invite everybody except Steve to go on mute, and I'm going to introduce Steve Emert.
Okay. Thank you, sir. So anyway, as I mentioned, this is the source for the presentation, and I really wanted to go through things, even though I'm not going to go through things A through Z, I do happen to start with an A word. So I'll try to go through quite a few different topics and try to group the topics together, as opposed to just going literally A through Z, where it could be two totally unrelated topics that happen to have letters that start words that start with the same thing. So anyway, we'll start out with angular dimensions and kind of work around that. So this one should be pretty obvious to everybody because we've been using these all our lives, but just to put some words to it. So we do use, of course, degrees, which is a 1/360th of a circle. We also use, because astronomical objects are so far away, arc minutes and arc seconds. So arc minute, as opposed to just a minute, which is 1/60th of an hour. An arc minute is 1/60th of a degree, and arc seconds, instead of a second being 1/60th of a minute, 1/60th of an arc minute. So the part of this that I usually forget is, okay, which one do I use a single quote and which one do I use a double quote for? So you can see the single quote is for minutes and the double quote is for, minutes, and the double quote is for seconds. One thing I just learned actually about an hour ago, where did the words minute and second come from? And it turns out minute comes from Latin, pars minutia prima, which I'm probably butchering, and that means first small part. And so, with hours and within hours, that's the first small part of an hour. And then seconds means second small part, or in Latin, pars minuta secunda. So I thought that was kind of an interesting segue there. So anyway, that's basically the angular dimensions that we use. Now, one thing that especially important to learn as we're starting out in astronomy is, how do I figure out how big that thing is up in the sky? So basically, if you use your little finger, and the nice thing is you're doing this at arm's length, so that, in my picture here, at arm's length. So even though you may have bigger hands and bigger fingers and everything than normal, that usually equates to you have longer arms. So it works out that, your pinky finger is about 1 degree. So that's about twice the apparent diameter of the sun and the moon. 5 degrees is 3 fingers together. 10 degrees is the width of your fist. 15 degrees, you can kind of go, I'm having a hard time doing that, your first finger and a little finger. And then 20 degrees or so is if you stretch your thumb and your forefinger way out, so that you can look at things up in the sky pretty easily. Just looking at a couple of those items, I thought it was kind of interesting as I was putting this slide together that, the Big Dipper a little bit over 20 degrees, so about 25 degrees end to end. Turns out that if you look at Gemini, that's about 20 degrees end to end. and so is Cygnus, another 20 degrees end to end, as well as the Orion, the main part of Orion, the hourglass. So anyway, you can see those large shapes are about the distance held from your little finger to your thumb up in the air. When you get into the individual objects, of course, the moon is a half a degree, give or take a little bit, and the sun is also a half a degree, a little bit. And then we get into much smaller things. If you look at things like the Ring Nebula up in Lyra, that's only 1.4 by 1.0 arc minutes. And the little dumbbell is 2.7 by 1.8 arc minutes. So these are really small items, of course, in the sky. So moving to the other end of the alphabet, Zenith, and associated with that is nadir. So Zenith is that point directly above you. And you'll tend to use that a lot if you're looking at astronomy programs, because it'll point to zenith, and nadir, the imaginary point directly beneath you, pointing to the center of the Earth. About the only time I ever see the word nadir show up is when I'm using one of the astronomy programs, whether it's Carte de Ciel or Stellarium or any one of the commercial ones, because generally we don't do much pointing straight down to our feet, but we do look up straight at zenith directly above us. Related to that, we have the meridian. So the meridian is the highest point any object can be in the sky as it traverses the sky. Also, you can see the bonus in their culmination, the moment when the celestial object crosses the meridian and is thus at the highest above the horizon. So basically, meridian is that line from directly up north to directly south, and as the object passes from east to west across the sky. Now, related to that, the main reason that we use meridian is our telescopes. If we have an equatorial mounted telescope, you have to worry about the meridian flip. One thing that wasn't obvious to me as I was starting out a long time ago, that you had all of these weird angles on an equatorial telescope mount. And one thing is, generally you never let the counterweight go up above horizontal or the telescope tube go down below horizontal. You can see the reason for that, of course, is if it keeps on going, because we're looking at south in this picture with east to the left and west to the right. So if it continued rotating that way, you'd see the optical tube assembly eventually ram into the mount. So as an object goes from east to west, it'll eventually end up flipping. So the whole telescope flips all the way around with the counterweight pointing to the other side and then starting over. So that's one of the things that it's always a little bit frustrating if you're looking at something in the sky and it's just a little bit east of the meridian, and then you want to slew to something that's just a little bit west of the meridian, and you're expecting it to just, move 5 or 10 degrees or something like that. And you see the whole telescope flip all the way around, and takes about a minute to flip around to the other side, but it's definitely necessary. So that's the main thing I think of when I see the word meridian. Related to that is the prime meridian. That's the north-south line on the Earth, which defines a 0 hour of latitude coordinates. I hate reading slides, even though I just did that. But pretty much everybody knows what the prime meridian is. And here's a picture of me standing on the prime meridian with one foot in the Western Hemisphere and one in the Eastern Hemisphere at the Royal Observatory in Greenwich, UK, a couple of years ago when I visited the place. So I see some things up there in there. So why don't I stop for a second before I flip on to something else? So Yara, you were asking, so every object has its own meridian, and Suresh, you already answered that. So I think I will shut up and let you pipe up when you need to, because it looks like you're answering them in the
Sure,
chat anyway.
I'll answer what I can, but otherwise I'll ping you, Steve.
Okay, sounds good. Now, one interesting thing that I found out after I'd visited the place, otherwise I would have tried doing it, was that that is the prime meridian, and the prime meridian is where I was standing, is in the middle of the observatory complex on the left-hand side of this picture. But we can all pull up a GPS on the maps on our cell phones, but the GPS is a US system. And because the Earth isn't exactly perfectly spherical, it's this oblate spheroid, and it's got a little bit of a bumpiness to it, not much, but a little bit. But the when the U.S. Army created the Army, whatever it was, the U.S. government created the GPS system, they picked a spot in the United States, Johns Hopkins University toward the East Coast, as the zero reference for the GPS system. As a result of that lumpiness and the fact that their reference is, about 6 hours of rotation away from the actual prime meridian. The prime meridian, if you were to take your cell phone and show the 00 coordinates, it'd be over probably about 30-40 yards away, about 20 or 30 yards away from the actual prime meridian. And if you're interested in that, I learned that from Tom Scott. He is a guy on YouTube that he's a British guy, and he does a lot of videos about various things, interesting places on the Earth, and it was his YouTube on that. So if you want, just do a YouTube search for Tom Scott Prime Meridian, and you'll see where this came from. So anyway, moving away from meridians, but kind of related, Polaris. So Polaris is the pole star or the North Star. Now, one thing that has come up quite often, because we've all heard of Polaris, even if before we became amateur astronomers, we think that's the most important star in the sky. So, geez, it must be the brightest. And it's not even close. It's only a second magnitude star. But it does, of course, have the advantage of being up in the northern sky for us, because we're at the 45th, basically at the 45th parallel, 45 degrees of latitude. Polaris is at 45 degrees, and it's basically right straight north. So that's cool for us in the northern hemisphere. Poor saps down in the southern hemisphere don't have an equivalent South Pole star. They have to do a little bit of extra work to polar align their telescopes. So related to the pole star and polar alignment and all of that stuff anyway, there's the term circumpolar. So circumpolar references the constellations that never go below the horizon. So again, because we're at the 45th parallel, anything that's within 45 degrees of Polaris never goes below the horizon for us. It just rotates around Polaris. So you can see the major constellations up in the northern hemisphere that are circumpolar: Ursa Minor, Cassiopeia, Draco, Ursa Major, Cepheus, Perseus, and Camelopardalis. Related to that, the ecliptic and the celestial equator. So the ecliptic is the path among the stars traced by the sun throughout the year. So basically, since the whole solar system formed, starting with the sun, and as all of the materials collapsed, they had that rotational energy. So everything lined up pretty much within a few degrees of the same horizontal plane around the sun. So we pick the one that the Earth's plane is the ecliptic. And then all of the other planets are pretty close to the ecliptic, except the dwarf planet Pluto, which really isn't a planet, it's a dwarf planet, so it was a captured Kuiper Belt object. So that's quite a bit away. Looking at this picture, you can see that small red circle is the ecliptic, because that's the Earth's orbit around the sun, and the large red circle in here is the ecliptic. Now that's different than the celestial equator. So if you take a globe of, a globe and look, you've got the equator line going around that globe. You extend that out into space, and that's the celestial equator. The celestial equator is not the same plane, because we're at a 23.5 degree tilt from the ecliptic. The celestial equator is also tipped at 23.5 degrees from the celestial equator is tipped 23.5 degrees from the ecliptic. I wasn't sure if I was saying it right. So anyway, that's why those two are different. So you can see the white line on this is the celestial equator. So related to that, we've got the Tropic of Cancer and the Tropic of Capricorn. Tropic of Cancer is the northern point, that the latitude line that the sun will appear north of the equator. So again, 23.5 degrees. Tropic of Capricorn is 23.5 degrees south latitude. So again, that's the line that marks how south the Earth can go, or excuse me, the sun can go in the sky. And since I mentioned 23.5 degrees north and south latitude, declination and right ascension are sort of related to that. That's not the Earth's reference. That's, of course, latitude and longitude, which I'll cover in a little bit. But declination and right ascension are the reference system for coordinates of objects in the sky. Or declination, that's the angle measured north or south of the celestial equator. So I happen to be looking south as I'm here. So 90 degrees up north is back behind me. So in front of me is 40, above is 45, give or take, and 90 degrees is ahead of me, pointing toward the south. And that angle is, of course, measured in degrees, arc minutes, and arc seconds. The rate ascension is the angular distance eastward around the celestial equator from the sun, starting at from the sun at the March equinox. So looking at that a little bit, you can see the north celestial pole is pointed at 90 degrees declination. What would be more or less straight above us when we're at the right time of the year would be 45 degrees, and then down is 0 degrees. So from our location here in the Twin Cities, we can probably see down to, what, Suresh, about 25, 30 degrees south, south declination.
Well, theoretically, we can get down to 45 south.
Okay.
It's 40, because we're 45 north, it's minus 90 degrees. So it'd be minus 45, but what you're saying is correct. We really, for all intents and purposes, we really can't go below minus 30.
Yeah, good point. Yeah, minus 30 because of all of the obstructions and everything. But yeah, you're right. Theoretically, minus 45 rather. So anyway, the rate ascension, to show that pictorially here. So you can see the 0 hour, 24 hour at the top, and that's going through, well, it's right at the edge of Cassiopeia. Now, this is where clocks and all of that differ from degrees. You know, we're going, rate ascension is defined in hours, arc minutes, and arc seconds, as opposed to degrees, arc minutes, and arc seconds.
Hey, Steve, can I stop you just for a second?
Sure.
Sorry, my neighbor's dog ran off and I had to go chase it down the street. Brandon had asked a question, is Polaris as north, meaning north straight over our heads, or in the direction north?
Polaris is definitely up in north, in the direction north. It's directly north of, let me back up a picture or two. It's directly north at the North Celestial Pole. So over our heads would be where I've got that line drawn pointing more or less toward 45. And the North Celestial Pole is where Polaris is, and that's directly over the North Pole of the Earth. So again, right ascension, this map that I pulled up only goes down to 30 degrees north declination, so it doesn't go down very far. So you can see on the right-hand side, it goes down to Auriga, not very far, and Perseus. So it's really showing just a little bit more than what's circumpolar. But anyway, the main thing is it's showing that the 0 hour starts at one side of Cassiopeia, basically, and then we divide the entire sky up into 24 hours. And you know, some of the more southern ones that it goes through are Hercules, Ophiuchus, Scorpius, and Sagittarius. Those are the 18-hour line. So that's part of the reason why since it's the 18-hour line, if you notice, Hercules, Ophiuchus, Scorpius, Sagittarius are all summer constellations. And stuff up near the 0 hour, well, okay, let's go 6 hour, touching Orion. That's more of a winter constellation. So you can see they're located in different parts of the sky based on their time. Let me see, am I in the right spot? Declination, right ascension. Okay, so going back to the Earth, of course, latitude and longitude. So latitude's easily determined by measuring the angle from the horizon to the specific star, the sun, using a sextant. So that's the north-south. That's the declination is the sky equivalent of latitude. And longitude is a little bit more difficult since we're turning once every 24 hours. You have to know the time accurately to know where you are in relation to the prime meridian. When we're not doing daylight saving time, we're 6 hours away from the prime meridian. Right now, we're 5 hours from the prime meridian because of spring ahead in the spring. The interesting thing on this, there's a really good book by Dava Sobel that's just called Longitude, and it talks about the quest for being able to determine, accurately determine your latitude when you're out at sea. So the Longitude Act of 1714 authorized up to a 20,000 pound prize for creating a timepiece accurate enough to determine the user's longitude while they're at sea. And this is also some pictures I took in the Royal Observatory in Greenwich. H1 is this big pendulum one, and it was actually running there under glass, but it was running. That one was first tested at sea in 1736, and it was accurate enough to win a little bit of the prize, enough money that it could keep on developing things. So we kept on working with trying to account for motion of the ships when they're at sea, and the different temperature and different climatological changes and stuff. So his H2 and H3 were marginal improvements, and he didn't finally really have success until he came up with this overgrown pocket watch, H4, that was successfully tested in 1761, and he won most of the rest of that $20,000 prize. There were some other people in there. If you go to look at the Wikipedia article on Longitude, you'll see that there are a number of other people that were creating some things and won some portion of that 20,000 pound prize. But Harrison did the most of it, and that, again, that's really documented in a pretty interesting fashion in Longitude by Dava Sobel. So since we're talking about those movements in the sky, equatorial mounts for telescopes. So those are aligned to the celestial North Pole. So it's kind of hard to tell. I should have put a line through this, but the axis of this, these telescopes are pointed at the North Pole right now. So we align the telescopes to the celestial North Pole, or South Pole if we were in the southern hemisphere, of course, and it rotates around that axis then. So you can see these are set for something close to 45 in these pictures. And then in order to track the sky, they only have to move in one single dimension, in one axis, just in the right ascension axis. So going back, altitude and azimuth. So altitude, of course, is the vertical direction. Now we have alt-az scopes, which I'll show in a second, but altitude is vertical direction from 0 at horizontal up to 90 degrees vertical. And then azimuth is 0 to 360 degrees, not hours, minutes, seconds, around horizontally. So we really do a good job of screwing up all of this measurements and making it complicated to try to find something, don't we, as I'm realizing as I'm going through all of this stuff. But again, altitude is vertical direction, azimuth is horizontal direction, and these are all in typically just measured in degrees. So of course, alt-az telescopes include Dobsonian telescopes, like on the right, or tripod mounted up, down, left, right altitude azimuth scopes. These, of course, as objects go through the sky, you have to do a little bit of movement both in the vertical and the horizontal direction in order to step it, because nothing goes straight across the sky. Related to that is another term that's kind of an informal term called Dobson's Hole. John Dobson, of course, is the creator of the Dobsonian style telescope. Here I'm showing a picture of, I think it's our 25-inch scope up at Long Lake Conservation Center. But when you get up to 5 to 10 degrees or so of the zenith straight up, it's really difficult to aim it, because you're having to twist, something that would be normally just moving it vertically in altitude. You have to do some twisting around and then come up, and it just gets to be a really big problem. So Dobson's Hole is also a big problem for very large Dobs when you have to use a ladder. And also the problem is too, with a really big scope like this, it's straight up. In this case, it's probably about 8 or 9 feet straight up. So it's kind of hard to see near Dobson's Hole. What are we looking at? Constellations. So we're down to the C's here through a roundabout way. Constellation is another one that's pretty obvious. It's a group of stars recognized by the Astronomical Union, the astronomical community. Started out of course, in antiquity depicting a person, animal, or object. And most of them in the north are based on Roman mythology. The ones in the south are based on some newer terms. You know, down in the southern hemisphere, you're going to see things like telescopium, fornax, which is furnace, things like that. So the interesting, or whatever, one thing that's may or may not be interesting, but it's a fact, is, you know, instead of just being the collection of stars that were based on this mythology way back in, you know, the early days, in the 1922, when we came up with the modern list of 88 constellations, it's defining an area of the sky. So everything that's in the lighter color here is part of the constellation Orion, not just the larger stars, you know, Betelgeuse and Bellatrix and Rigel and so on. Oh, and I see, Suresh, you mentioned that John Dobson, yeah, he is definitely probably one of the most important amateur telescope makers. And he also signed my mirror cover on my Dob. So I was going to grab that thing for this, but I forgot to do that. Okay, related to constellations are asterisms. Now here I've got a number of pictures of some pretty large asterisms. So you can kind of think of, on the right-hand side of this picture, the summer triangle as being an asterism. That's actually 3 stars, the 3 major stars in 3 of the constellations in the summer, Deneb in Cygnus, and Vega in Lyra, and Altair in Aquila, whatever. I always say it the wrong way, I think. But anyway, you can think of that summer triangle as a constellation, as an asterism. Cygnus itself is often called the Northern Cross, which also can be thought of as another asterism. The Big Dipper is, of course, the major stars of Ursa Major, but the Big Dipper itself is not the entire constellation of Ursa Major. It's only the asterism of the Big Dipper, whereas the Little Dipper is all of the stars of the Ursa Minor constellation. So sometimes the asterism lines up completely with the constellation, and sometimes it doesn't. The Teapot is the major set of stars, in the most recognizable set of stars in the constellation of Sagittarius, of course. But those are really big ones. Way up at the top of this, I only picked one example of a small asterism. It's a coat hanger in Vulpecula. And there's a lot of asterisms. One thing that you'll do is star hopping, if you haven't done it already, is there's a lot of triangles in the sky. I'm always looking at things in a kind of a triangle asterism as I'm star hopping from one spot to another. So since we're talking about constellations and asterisms and stars, let's take a look, talk about the magnitude. So that magnitude, of course, is the brightness of an object. It started out way back in antiquity in the ancient Greeks as a pretty imprecise measurement. They just came with magnitudes 1 through 6, and it was an object of the first magnitude, an object of the second magnitude is dimmer, and so on up to the 6th magnitude, which is pretty much where you can stop seeing things visually. 1856, we formalized that, and so came up with the actual scales that the first magnitude star is 100 times brighter than a 6th magnitude star. And then when you divide that out into those magnitudes, each magnitude is about 2.5 times as bright as the star of the magnitude, 1 magnitude down. So, you know, 1 is 2.5 times brighter than magnitude 2, which is 2.5 times brighter than magnitude 3, and so on. So just giving it a little bit of context for that. You know, in this chart that I grabbed, they're saying magnitude 7 and above is not visible with the unaided eye for the most part. The sun, hugely bright, obviously, magnitude -26. A full moon, again, hugely bright. That's why we have moon filters with a magnitude of -12.5. You get on the chart on the bottom there, you can see the Hubble Space Telescopes can see down to about magnitude 28, whereas we can only see down to about magnitude 6. And the brightest star in the sky is Sirius at magnitude -1. And Venus gets to what, about -4.5 or so when it's at its brightest. So basically most everything we're looking at, all the deep sky objects, are typically magnitude 8 and darker, which is why we're using telescopes. One thing about magnitude is we're looking at the visual magnitude, but the trouble is it can be a little bit misleading. You know, if it's a star, it's pretty straightforward. You know, the brightness is what it is because it's a point source and that's what it is. But you can take a look at galaxies or diffuse nebula, things like that. That magnitude is a little bit misleading because you've got the surface magnitude. And for example, M33, the Messier object 33, the galaxy, that one is angular size 60 minutes by 30 minutes, which means it's twice as wide as the full moon and as tall as the full moon. And its magnitude is 5.7, but that's its surface magnitude because it's so diffuse and spread out over, you know, basically an arc minute by a half an arc minute of space. It's really almost invisible unless you're really in good skies. Though all of that stuff was the apparent magnitude, how bright it looks like to us, whether it was surface magnitude or just magnitude in general. The absolute magnitude is another term that's used. We don't use it so much in amateur astronomy, but they need to know what it is for professional astronomy. Well, the absolute magnitude of an object is what the apparent magnitude would be if it was 10 parsecs or 32.6 light years distant from us. You know, not accounting for, that's just extinction due to the distance, not, you know, gas or dust or anything like that. So since I mentioned both parsecs and light years in that previous slide, the distance measurements of parsec and a light year. So parsec is parallax of 1 arc second. And of course, from one side of Earth's orbit to the other side is, you know, the sun's here and, you know, 93 million miles that way and 93 million miles that way, 186 million miles. So we look at an object when we're, say, January 1st and June 1st, look at an object and compare it to the background stars behind it and look at the parallax, how far it's moved. We can see that 1 parsec is 3.26 light years distant. So the next nearest star, Alpha Proxima, is what, 4.3 light years away. So it's probably about 1.5, about 1.5 parsec away. And conversely, light years, that's the distance it takes light to travel in 1 year in a vacuum. Of course, light travels more slowly in physical mediums. Personal note on that one, while I was a technician, mainframe engineer, I had to do some stuff with my oscilloscopes, doing some timing of clock pulses and stuff. And that's when I found out that in copper, at least, that's 1 light second, about 12 or 14 inches is 1 light second in copper. So a light year, you know, 6 trillion miles or 9.7 trillion kilometers. So it's interesting when you get down to a billionth, it's there. And of course, parsec, I had to bring this picture in here. Parsec is a measurement of distance, not of time. So that's why all of the hardcore Star Wars fans came up with, okay, well, they justified something about how many stars you'd have to jump and whatever to do the jump to make the Kessel run in less than 12 parsecs. Since obviously the distance to wherever the Kessel run goes to is the same distance all the time. Anyway, on to something in reality again, the Bortle scale. So since we're talking about the brightness of stars and the brightness of various things, let's take a look at the brightness of the sky. So the Bortle scale was created to determine, to quantify how bad or how good the light pollution is in any given area. So they came up with this 9-level numeric measurement of the night sky brightness. So in the middle of downtown Minneapolis or St. Paul, it's an 8 or 9. You get out to the suburbs here, so we're either 6 or 7 for brightness, maybe down to 5 if we're lucky. We get out a little bit farther, and we can see more and more of the stars, and you get to a perfect dark sky site, and that's a Bortle 1. So the larger the number, the worse it is. So let's put this in context a little bit for some of our viewing sites. So Metcalf, of course, is a suburban site, and that kind of straddles between Bortle 6 and 5. Joseph Casby, it's always amazes me when I go, move from Metcalf out to Joseph Casby and look at the sky. Even though it's about a mile away from Metcalf, it's visibly darker. It's, it's still suburban skies, but it's visibly darker. We move out to Eagle Lake, of course, and it's 4, kind of bordering on 5. So that's a little bit better suburban skies. When we get down to Cherry Grove, which when I joined the club in 2001, that was our dark sky site. And of course, it's gotten worse since then because the towns around have built up and built more lights. But anyway, that's still a pretty dark sky site. We can definitely see the Milky Way from down at Cherry Grove, where it's a little bit more difficult. You just barely see it from Joseph Casby, and I've really never been able to see the Milky Way really well from Metcalf at all, unless I get a really good night for some reason. Some of the one of the non-MAS sites, Crex Meadows up in Danbury, Wisconsin, that one's a little bit darker, and so that's around about 3. And then when we get to our Long Lake Conservation Center, which is the MAS's darkest sky site, that's 2, kind of bordering on 3, but that's really a good dark sky site. I think even though the maps that I picked this reference point from said that it's between 2 and 3, to me it looks more like a good 2, because we've been able to see really dark stuff. One time I was up there, I was actually looking at dark nebula, and I'm just seeing this black hole in the sky. I cannot see that from anywhere closer to the Twin Cities. When you compare the darkest sites in Wisconsin from the map and the darkest site from Minnesota, the one in Minnesota is up in the Boundary Waters Canoe area, right up on the Canadian border, and the darkest Wisconsin site down in the National Forest, a little bit south of their northern border. That's what it looks like, the United States on the most current version of the map. And it's unfortunate that we have all of those bright reds and yellows up where we live. Someday I've really got to get down to the west. Okay. So anyway, moving back to some other things, looking at the Zodiac. So unfortunately, I'm not at the end of the alphabet, even though I've got a Z here. And I had to put in what's your sign. It always bugs me when somebody calls this the hobby of astrology. Astrology is what's your sign. Astronomy is science. But anyway, the Zodiac itself is that area of the sky around the ecliptic and 8 degrees north and south. And of course, there's the 12 constellations in the Zodiac. And Park Kunkel, this must be about 7-8 years ago now, he created a little bit of a controversy. And Park is one of our members, and he was also a member of the Minnesota Planetarium Society, and I think he was a director of it at the time. But anyway, he realized at that point in time that Ophiuchus is also located within the Zodiac. And, of course, whatever your zodiacal sign is right now, it's actually off a little bit because all of the signs were defined 2,000 years ago, and things have moved since then. But anyway, the Zodiac itself is that 8 degrees above and north and south of the ecliptic, and so that's where those constellations happen to reside. That will change. So precession is a related term. So that axial precession is that change of the orientation of an astronomical body. The one that we know best is, of course, our own, the Earth. And we're tipped 23 and a half degrees to the ecliptic. But one thing that happens is, just like a top that rotates, does anybody play with tops anymore? Just as a top rotates and, it kind of wobbles a little bit, and that kind of defines a circle around above it. The Earth does the same thing. Our circle happens to take 26,000 years to complete. This is the path that it takes. So you can see right now, its Polaris is basically at the center. It's a little bit off, not exactly, but you go back 4600 BC, it was down in Draco. You move forward in time to 8400 AD, so another 6,000 years from now. I can't even see what it is, but anyway, it's up there. And then 1400 and 900 AD, it'll be way off to the side. So we just happen to have Polaris being our pole star right now. It's going to change, so you get 16,000 or 12,000 years in the future, and Vega is going to be pretty close to the pole star. So related to all of that kind of stuff. So let's take a look at the term equinox. That's the point on the celestial sphere where the ecliptic crosses the celestial equator. Actually, I think of it not as a point as much as a time. The equinox, the vernal equinox in the spring and the autumnal equinox in the fall. It's when the sun crosses in the spring, the sun crosses the ecliptic moving north. And in the fall, it's when the sun crosses the ecliptic moving south. So again, the sun appears to be, either up 23.5 north of the equator or 23.5 south of the equator. Solstice, on the other hand, is those opposite points. So the summer solstice is when the point on the ecliptic when the sun reaches its farthest north point, June 21st, and in the winter it goes the farthest south, and that's on December 21st. So of course, as we all know, that summer solstice marks the actual beginning of summer, and winter solstice marks the beginning of winter for us. A couple of other terms here. Opposition. So we'll get back into looking things in the sky instead of what's happening on the Earth. So if you take a look at something, that the opposition is when the object is directly opposite the sun in the night sky. So that's why my sign is Scorpius, and my birthday is October 31st. So that's late fall kind of, and so the sun is actually in Scorpius then. Scorpius is a summer constellation. We can see that right now. So so this opposition is basically just the opposite end of what your astrological sign would be. So let me think about it. What else do I want to say about that? So anyway, opposition is when the object is highest in the sky at midnight. So that's the best viewing for us is an opposition. Unfortunately, right now, Jupiter and Saturn are both relatively close to the sun, so they're nowhere near opposition. They're closer to conjunction at this point in time. So conjunction, the other half of that thing, when two or more objects appear very near to each other in the sky, as all of the planets and everything are moving, the planets are moving in right ascension as they go around their version of the ecliptic. That conjunction happens when they move together in right ascension. You've got both superior conjunction and inferior conjunction. So superior conjunction, so if you take a look at, from our point in Earth, we look at Venus and the sun, or Venus and Mars. Try that again. Venus and Mercury, two M words. Those could come together and have an inferior conjunction, whereas you can have a superior conjunction with Saturn and Jupiter. So one, of course, that we just remember because it just happened back in December, that was the Jupiter and Saturn great conjunction on December 21st, about 7 p.m. So that one's a picture. I cheated on this right-hand side of the close-up where you can see Jupiter and Saturn together. The moons of Jupiter don't look that bright. This I just stole out of Stellarium instead of taking an actual picture, since I'm not an imager. But it was really that impressive through the telescopes if you managed to catch it on that particular day. So anyway, related to inferior and superior conjunctions, we've got inferior planets and superior planets. So that one's pretty straightforward. And this inferior planets are closer to the sun than us. So Venus and Mercury are inferior to Earth, and Mars, Jupiter, Saturn, Uranus, and Neptune are superior to the Earth. So if you move to a different planet someday in the future, if you're in Jupiter, only Saturn, Uranus, and Neptune would be superior planets, and everything else would be inferior. Occultation. So, and occultation is when something occults it on the moon, when one object is hidden by another one closer in front of it. So the moon can, of course, occult stars. Quite often occults the Pleiades, or at least big portions of the Pleiades. And of course, informally, an occultation is when a taller astronomer or his telescope blocks your own point of view. He's occulting your view of the sky. That never happens. Maybe with our big scopes, the bad, and the other big Dobbs that we have. So related to an occultation, an eclipse, when the nearer object completely covers the farther object. Of course, whoops, it backed up. I didn't do that, I promise. Anyway, of course, the lunar eclipse is when the Earth is between the moon and the sun, so it's eclipting the sun. I try that again. A lunar eclipse is when the Earth is between the moon and the sun, and the moon is being blotted out by the Earth's shadow. And of course, the solar eclipse is when the moon is between the Earth and the sun, much smaller space. So of course, the last time that we saw it here in the United States was August 17th, 2017, when most of the MES was in either Nebraska or Utah or Wyoming. And the next time it's going to happen is going to be April 8th, 2024, moving up. And I know I'm going to be down in Texas that day, but it moves up closer through Indiana. Actually, it runs right through Indianapolis, Indiana. So that'd be a good second place probably to go. So related to the lunar eclipses, most especially, is Umbra and Penumbra. The Umbra is that area of total darkness in the shadow caused by the eclipse. So the diagram on the right-hand side of this picture shows where the moon is in the darkest portion of the shadow from the Earth. So that's the Umbra. Pictorially, that's showed by that dark red moon in the middle of this picture. And then the Penumbra is when it's only part of that light is passing through from the eclipse. So the two moons to the left and right are those the Penumbra. Related to an eclipse, again, a transit is when a smaller object passes in front of the other. So two really famous transits are, of course, the Mercury transiting the sun and Venus transiting the sun. So Mercury transits the sun a lot more often than Venus does. So the last 4 times, 2003, 2006, so 3 years, then it skips 10 years, so 2006 to 2016, then it backs down to 3 years again, 2016 went to 2019. Next time around for us is 12 years apart, so 2032. So we can at least look forward to that one in our lifetime. If you missed the last 2 previous transits of Venus, June 2004 and June 2012, you might be out of luck unless we really have some good things happen so we can live a long, long time, because the next time is 2117. So again, it has 2 close together, and then it waits a long time, a little over a century, and then it has two close together. And I know we've had a number of good talks within the last couple of years about how all of that timing works out for the transits. To ones that you can see a little bit more often, the Galilean moons of Jupiter. So the Galilean moons, of course, are the ones that Galileo was able to see when he first looked through the telescope in 1609, 1610, in that time frame. Io, Ganymede, Callisto, and Europa. And the shadow transits are the actual shadows, which are a lot easier to see because of the contrast. So here you can see Ganymede on the left, Europa on the right, and Ganymede's shadow is the one at the 1 o'clock position right up at the top at the edge of Jupiter, and then Europa's shadow is that little one a little bit lower than that. I probably should have put this together with a couple of other terms. I think I might have gotten this one out of order, but greatest elongation. Greatest eastern elongation is when a planet is farthest east in our sky from the sun. Greatest western elongation is when the planet is farthest west from the sun. Maybe should be fairly obvious. Generally, we only talk about that with Mercury and Venus, since their orbits are inside the Earth's orbit and they never get very far from the sun. We can't have Venus or Mercury at opposition because we can't get it on the opposite side of the sun from our position.
Hey, Steve, can I stop you for 1 second?
Sure thing.
There's one thing about Jupiter. If you can go back 1 slide.
I will. Oops,
I threw this in the chat, but I want to make sure people know
I
that.
lost this. There we go. Sorry about that.
So Jupiter, so like every planet, Jupiter has an axial tilt. Every 6 years, Jupiter's plane is even with the plane of the solar system. And the reason I'm bringing this up now is because this is one of those years. When this happens, not only will we see the moons cross in front of Jupiter, like Steve's picture here, but the moons actually will eclipse each other. And there is a listing out there on the internet you can find if you want to see something like this, where the moons will actually block each other out or pass in front of them, behind them, etc. Their shadows will cross each other. So this is a really good year to be looking at Jupiter's moons.
Yeah, very true. Now, and one thing, even though Jupiter's axial tilt must not be very much, because they always look like they're in pretty much a straight line, even no matter where they're at in their orbit. Pardon?
Yeah, it's 3 degrees.
Okay, yeah, so 3 isn't too bad. All of the moons always look like they're pretty much in a straight line. Unfortunately, Saturn's got a lot more axial tilt, and so its moons, when they're rotating around, they just look like they're stars somewhere nearby Saturn. They're not in a nice straight line like they are for Jupiter. Because let me go back to because here you can see that, that's a picture from Stellarium, but still all 4 of the Galilean moons are really close to a straight line in this diagram. Whereas if you look up at Saturn, I can only see 2 of the moons, but they're maybe 3 if that one's a moon way off halfway between Jupiter and Saturn up at the top, but they're nowhere near in a straight line. Okay, transit Galilean moons and shadow transits. Okay, so greatest elongation I kind of mentioned already. Quadrature, kind of related to that. Shresh, do you ever use quadrature? It's a term here, but I've never really used it for anything practical that I do.
I don't. I just think of it as the planet is halfway to leaving the sky. That's really all I think about when I think of quadrature.
Good point. Yeah, because it's halfway to opposition, which would be, in this picture, if this must be depicting Mars because it's not too far from Earth. So if it were straight down at the bottom, it would be in opposition. So it's halfway there.
Yeah, exactly.
Okay. Because of that stuff, I guess we need to talk about prograde and retrograde motion. So retrograde is when the planet appears to be moving in the opposite direction that it normally does from night to night. So in other words, everything normally moves from west to east in the sky over time. The sky itself is moving from east to west, but everything in it is going the opposite direction. But retrograde is when it's moving from east to west, as compared to prograde, the normal motion, which is from west to east. So just looking at that pictorially, grab these couple of pictures of Mars in retrograde motion at 2 different times. So in the left hand, both of these pictures, it starts out with the earlier date is on the right hand side of the picture. It's moving, then all of a sudden it reverses back around, and it's not in a straight line, of course, because Mars isn't exactly on the plane of the ecliptic. So depending on where it's in its orbit and where we're in our orbit, as it goes into retrograde motion, it may make that loop, or it may make that S-curve shape. Okay, so moving a little bit close in, the moon phases. So the terms associated with moon phases, we've got the new moon, obviously when it's all dark. The sun is on the opposite side of the moon. Waxing is when it's getting larger. The first quarter moon depicted here, it's lit up on the right-hand side of it. Full moon, of course, when it's fully lit, so the sun is behind our position, so we're looking at it on the same thing. Waning is when it's getting a little bit thinner, and then you get to the third quarter where the left-hand side of the moon is illuminated. Related to those, gibbous. So gibbous is when it's more than halfway, but it's not fully illuminated. Gibbous, Latin for hump, and then crescent is what it says. It's a crescent moon, and of course, with all of those terms, let me move back to that picture. So you can see different portions of the moon is in shadow, and the sunrise or sunset on the moon is there at that terminator, and that's where all of the good things to look at are, because we're seeing the long shadows of the craters and the mountains along the terminator.
Hey, Steve,
And
Michael Cowper just asked a question.
Earthshine. Why don't we see Earthshine during the new moon? That's we should actually. Why don't we? That's a good question. Why don't we see Earthshine during the new moon?
Because it's too close to the sun. In the sense that the elevation of the moon, when we can see it in the evening sky or what have you, is too close to the sun.
Yeah, good point. Okay.
Otherwise, he'd be right.
Yeah. Yeah, because they're basically, a new moon. The sun's there and the moon's here, so yeah, they're going to be really close to each other. Okay. You do see the Earthshine, which of course was the next one. When we have a crescent or thereabouts, we can see, like in this overexposed picture, we can see the Earthshine coming off the moon, off the Earth, the light reflected off the Earth onto the moon.
It's something we can see tonight.
Yeah, should be able to. Okay. Moving around to some other things, the rings of Saturn. We've got the Cassini division and the Encke division, which I believe were the reason I put this in here. So basically the rings of Saturn, as we know now, they're ice particles around Saturn, and it has a 27-degree tilt from the ecliptic, as opposed to 3 degrees that Suresh just reminded me of. So the rings do appear to change from year to year. They're going to disappear. It's going to be edge on to us March 2025. So we've got a few years before it basically disappears from us. Okay. Getting kind of toward the end here, we're looking at some of the other terms. Twilight. Twilight's kind of a misunderstood term because, it's like, well, it's starting to get dark, but there's specific definitions of twilight. There's civil twilight just after sunset. And that's when and it's defined as the sun is from 0 to 6 degrees below the horizon. And then it gets to nautical twilight, which is between 6 and 12 degrees below the horizon. And then astronomical twilight is 12 to 18 degrees below the horizon. And then finally it gets to be night when it's more than 18 degrees below the horizon. So as it's getting darker and darker and darker. If anybody is actually a beginner or new here, one thing to keep watch just after the sun is set, turn around and look the opposite way. Look to the east just after the sun is set, and you'll notice that it's really kind of dark right at the horizon, and then the sky gets a little bit lighter above that. Think of that. That's actually the shadow of the Earth that you're looking at, is that dark spot. So it's really kind of cool when you think about that. Something that I haven't been able to see up here, but I have seen when I've observed down in Florida, is a zodiacal light. It's a large, it looks just like this picture, really, not quite as bright as this picture because that's a little overexposed, but a large diffuse triangle shaped set of light it glow in the west after the sunset. Looks kind of like light pollution, but it's not. It's actually the light from interplanetary dust that's been scattered. So, as per my experience, you've best seen from southern latitudes, best seen in the winter and early spring. And when I've been down in Cedar Key, Florida, it's been in the winter time. And it's pretty dark skies, even though when you look back at that sky pollution map, the light pollution map, the place I was looking at from the Cedar Key, Florida, is on the Gulf Coast, about 2 hours north of Tampa, St. Pete, and you're looking out over the Gulf of Mexico. So even there's a lot of light pollution in the area. I'm looking straight south, and it's really good skies right there. So I'm sure that it's bortle 3, or at least bortle 3. It's probably more like bortle 2. In that place, but all of that stuff appears to be true based on what my experience having seen that is. One that's pretty obvious, we think. Meteors are basically just leftover garbage in the solar system from when it was created. Dust left over from comets as well, dispersed through their orbit and burning up entering the atmosphere. Really wanted to get to meteor showers and the radiant point or radiant in meteor showers. So we name all of the meteor showers for their radiant point. illustrated here. We've got the Geminids. So the radiant point, all of the meteors are coming from this one spot. Doesn't mean that you want to just sit there and look at Gemini during the Geminids, but look around from that area, because that's where they appear to be radiating from. Comets, of course, related to all of that stuff. Again, stuff that's in the solar system made up of dust, water ice, frozen carbon dioxide, various other organic or non-organic compounds. Most of them, well, all of the non-periodic comets originate out in the Oort cloud, way out, you know, a light year out or thereabout, orbiting, and they get perturbed and then come down from the Oort cloud and come near the sun, and then, you know, generally happen once or twice in their lifetime and then burn up. Obviously, there are the periodic comets, like Halley's Comet, that are orbiting, you know, within the inner solar system. But basically, that's the definition of a comet: dirty ice, dirty snowball. So related to that, because I just mentioned that the non-periodic comets can come out from the Oort cloud, which is way out there. Here's some of the distances. So the term for distances within the solar system is an astronomical unit. Very self-centered on us, because it's the distance between the Earth and the sun. So that's 1 AU. So of course, Mercury and Venus are less than that, 0.7 and 0.4. Mars is 1.5 AUs. And you can see Pluto out there at 39 astronomical units. So very self-centered thing from our standpoint. Speaking of orbits, aphelion, the point in a planet's orbit where it's farthest from the sun. So aphelion for Earth, about July 4th. Perihelion is where, there we go. Perihelion is where the Earth, the planet, in our case, the Earth, is closest to the sun. So that's about January 3rd for us. When you take a look at, so that was, so the root word of that, of course, is helion, Helios for the sun. So aphelion and perihelion refer to distances around the sun. When you get to distances from the Earth, so specifically for the moon's orbit or any artificial satellite, apogee is when it's farthest from the Earth, and perigee is when it's nearest to the Earth. So the G stands for geography or Earth. And anyway, so then moving on from orbits to deep sky objects. So this one, basically, DSOs or deep sky objects are simply anything that's farther out than the solar system. So star clusters, like open star clusters and globular star clusters. Hey, Suresh, do you call them globular or globular? I've heard both.
I call them globular clusters.
Yeah, I do too, but I've heard a number of people call them globular star clusters, which is actually pretty apt, because they are in a really tight globe, you know, anywhere from a half a light year across to a couple of light years across, depending on which globular star cluster it is. But anyway, we've got those. Other deep sky objects, of course, are nebula of all types: planetary, emission nebula, reflection nebula, dark nebula, supernova remnants. The Crab Nebula, M1, is a supernova remnant. You can see on the right-hand side of this, the Witch Head is a reflection nebula, because that's reflecting light from stars that are within the nebula or nearby the nebula. Emission nebula is where stars embedded within the nebula are actually exciting the gases, and the gases are glowing. And then, of course, the dark nebula are ones that are not being excited by the light, and they're basically just shadows within the cloud, the molecular cloud. And then, of course, there's galaxies, and there's a classification of galaxies. So most of them are the spiral galaxies. We see the different classifications of spiral galaxies. I'm not going to get into them too much, but you can see we've got spiral galaxies on the top, some that are kind of irregular galaxies toward the middle. The barred spiral, meaning that there's actually, it's a spiral, but there's a big bar in the middle of it. And as galaxies merge together, you know, you will lose those cool spiral forms and they become elliptical galaxies as everything merges together and they become just big nebulous blobs. So anyway, that's just a tiny bit on deep sky objects. Of course, go back to last month. If you didn't attend the BSIG meeting last month, Suresh went into a huge amount of information about that, and a lot better than I just did in this very short summary last month. You can pick that one up off of the discussion forums. So moving out from those terms, just a couple of telescope terms that may or may not be familiar to people. So for refracting telescopes, we have achromatic and apochromatic refractor. So basically, the lenses on the objective lenses on telescopes are basically like prisms, you know, because if you take the cross section of a lens, it looks like a prism, and as such, it's not going to focus all wavelengths of light at the same spot. So an achromat typically uses two types of glass, crown glass and a flint glass, ground differently, of course, and either directly attached to each other or potentially airspace, but they get most of the light coming together in one spot, but not quite. An apochromatic lens is one that does it one better, and it has three different lenses to get all colors, all wavelengths of light to focus at the same spot, so we eliminate the color fringing. One other way to get rid of color fringing is reflecting telescopes. So Newtonian reflector telescopes are ones that have, instead of a lens, they have a mirror. So the mirror at the bottom of the lens, at the bottom of the tube rather, and it focuses light on a secondary mirror, and then that puts the light out to the side to the eyepiece. Dobsonians are a subset of reflecting telescopes typically, because most Dobs are reflecting telescopes. They don't have to be, but for the most part, the Dob was created just because you can make mirrors really large, and in conventional telescope mounts that can become pretty klutzy to work with. So the Dob mount is one that's nice and easy to work with for large reflectors. Other telescope terms, we have a compound telescope. The most often known compound telescope is well, they're also called Cadiotroptic. I should have actually looked up how to pronounce that word before I got in here. Oh well.
Catadioptric.
Catadioptric. Thank you. I appreciate that. Anyway, Schmidt-Cassegrains are the ones. Oops, and I spelled that wrong too. I see. Schmidt-Cassegrain, take out the G on the end, scopes, and Maksutov-Cassegrains are two well-known types. The Schmidt-Cassegrain on the left, that has that aspheric corrector plate. It looks flat, but it's not quite flat on the left-hand side, but it's a folded light path. And the Mac on the right-hand side, it's similar, but it has that that much more deeply embedded meniscus lens on the front that that changes the light path. And overall, they're both the same, a similar folded light path. Macs typically have a little bit longer focal length than or at least focal ratio than a Schmidt-Cassegrain. A couple of other terms. I mentioned one already, the primary. So the primary is either the primary lens on the front end of a refracting telescope or the primary mirror on either a Schmidt-Cassegrain or a reflecting telescope. The secondary mirror on a Schmidt-Cassegrain is the one that reflects it back directly toward the back into your eye. The secondary mirror on a Newtonian reflector telescope simply moves it out to the side where your head's not going to be in the way of the focal point. So related to those terms, aperture. Aperture is the diameter of the primary or the objective mirror or the objective lens. Lens if it's a refractor. The focal length is the point where all of those parallel light rays come to a point, parallel light rays coming from the star or deep space object come to a point after being refracted or refracted or reflected from the primary. And as you can see on this picture on the left, I drew in those lines as if the secondary wasn't there. That focal point would be a little bit outside the telescope. So you could put an eyepiece right there. Unfortunately, you'd have this big thing occulting the light path, your head. So that's why we have the secondary mirror there. And of course, the focal ratio itself is the focal length divided by the aperture. And anyway, there's a lot more about telescopes, just as there were a lot more things to talk about with deep sky objects. There's a lot more to talk about telescopes and accessories. If you want to go back to one that I did, February 2020, I did a BSIG presentation selecting and using telescope mounts and accessories. You can find that one on the Beginner SIG forum. I don't believe that we did a recording of that one. Yes, we did actually. We did do a recording of that one, so I think that's available as well.
And cut in here for a quick second.
You bet.
And by the way, if anybody is coming to next week's BSIG observing session, we will walk through the different kinds of telescopes. We do that at all the observing events.
Good point. Just to expand on that a little bit, I don't think you really mentioned it, but one huge advantage of going to the Beginner SIG observing sessions is if you're just starting out with your scope, or you got one, inherited one from somebody and you don't know how to use it, or you're not sure that it's put together right, or there may be some collimation problems with it, bring it, because somebody's going to be there, whether it's Suresh or another person with more experience that can help you out trying to figure out what may be wrong with it, how to use it, show you how to use it, how to collimate it, stuff like that. So it's a good time to bring a scope that you're just trying to figure out how to use and get some experience there. So anyway, that is about it. I mumbled my way through a lot of the terms for that. And also, as I mentioned, I think at the beginning, I definitely mentioned it in the discussion forum topic. When I was doing a little bit of research, I grabbed a document from Celestron's webpage that went through a huge amount of what they said was astronomical terms, but it was really telescope and optical terms. So if you want some really more esoteric terms, go ahead and pull that thing down from the BSIG forum topic that talked about this meeting today. And with that, I'll turn it back over to you, Suresh.
Great, Steve. That was wonderful. I don't see any new comments in the chat. I know Michael was, Steve, would you mind going back to the retrograde slide for a second?
Sure.
Michael sent me a question about it.
Okay. Pop back here a little bit. That one?
Thank you, yes. So Michael, you were saying that you were asking about how this works. So the way I understand it, Steve, just if you want to chime in and just stop me, is remember the Earth, what's happening is the Earth is catching up to a planet in its orbit. So what's happening is the Earth is catching up, the planet is over here, but as the Earth is about to catch up and pass the planet, in our sky, the planet will appear to be doing a loop over several weeks and months. And then as the Earth passes it again, and the planet still has its forward motion, this is the path that it will take. Did I say that right?
Yep, that sounded like you said it right. Think of it like if you're going down the freeway and somebody is passing, you're in the left-hand, well, yeah, whatever. So you're in the right-hand lane, you're going slower, and someone's in the left-hand lane passing you. If you look at the landscape behind him, let's see. Yeah.
But
never mind. You can kind of make that work, but it's not really all that great. But anyway,
I know what you're trying to say.
Yeah. Anyway, it kind of works that way. But as he's passing you, you're going to see that his motion in relative to the stuff behind him is going to change, and that's what's happening here. That the stars can be thought of as being stationary in respect to the planet, and the planet moves from night to night because we're moving in our orbit, and Mars is moving in its orbit faster than us. So as we're moving, it's the relationship between them. So anyway, I'm not going to work waving my hands around here. Just
to add a little bit, as Steve said, think of the stars here as stationary because even though the planets may seem far away, they're right next door when it comes to comparing with the universe. So those stars are way out there. So they're not going to look like they move to us at all. But the planets being much closer, they will appear to move from night to night amongst the stars. And that's what Steve's showing here. Did anybody else have any other questions?
Okay. I don't see any other questions. Anybody want to bring up anything audibly? Go ahead and unmute and.
Yeah, feel free to unmute and ask, make a comment or ask a question, anything you'd like to do.
Thank you, and have a lovely rest of your weekend.
Thank you. Is that Yara?
Yeah, that's me.
Thanks, Yara. No, I think you covered it all pretty good, Steve.
Okay, appreciate that. And
so everybody, just another reminder, we'll be meeting up, weather permitting, next Saturday, April 24th at the Metcalf Field, which is near Afton. If you, Steve had mentioned earlier, if you have a telescope and you'd like to learn how to use it or learn how to set it up, feel free to bring it. We'll, of course, have telescopes on hand as well. And if you have any questions about that, feel free to drop me a note. Also, as I mentioned earlier, we are limited to 50 people and we're about halfway through that count now. So if you want to come, please do drop me an email or respond on the MAS forum if you're a member. And so I can add you to our list so I can keep you up to date on the weather. With that, I think that's everything. So I think we'll stop here. Steve, once again, I really appreciate you doing this. The next presentation will start up again in November. So the rest of this year will be about the observing sessions.
Hey, gentlemen, there's a star party at Eagle tonight, correct?
Yeah, sorry, thank you. I should remind you that. I should have said that. There's a public night at Eagle Lake Observatory tonight. The trouble is, I think they are, what's their limit now, Steve? Is it 25 or 50?
I think you said 40. I think you said 40 this time.
40. So these events fill up as well. So you'd have to check the MAS forum and contact Merle to see if they have space available tonight.
Yeah, now for the Eagle Lake ones, you do have to sign up on the Eagle Lake discussion forum. There's a topic there. The last time I looked early this morning, it was not completely filled yet. So there still should be some chances to get there.
Do you know if non-members can sign up in the forum?
I'm sorry?
It was at 30 at like 9 a.m.
Okay. Yes, that particular forum you can post to even if you're not a member.
Great. And I'll go see if I can find that real quick and I'll post that in the chat in case somebody's interested. One second. Any other questions while I'm doing that?
Okay, I think we got it. Michael, actually, you mentioned earlier, comets must be viewed from dark skies. That is true. No telescope needed. Yes and no. We had a bright one last when was that? Last fall that we could see without a telescope. But yeah, quite often comets are, you know, magnitude 7, 8, 9, depending on where they're at and how old they are and if they're a brand new one that's coming into the inner solar system or not. So. But it's really cool when you can see them without a telescope.
Steve, I don't see the listing that Merle usually has out here for signing up for the.
Okay.
You know where he puts it?
Hang on, let me pull up the website myself and take a look.
Normally he puts it right on the observatory discussions.
It's. Actually, oh, wait a minute. I may have lied on that one. It might be, let me sign in and it might actually be in the Eagle Lake Observatory.
Yeah, that's where I'm looking.
Okay, MAS Star Party is in advance. Public Star Party, April 17th. So it's the first one under MAS Star Parties and Events.
Oh, it's under there. Okay.
Yeah. So it's the first one after the announcements section.
That's why other people can get to it. Now I understand.
Yeah. Let me see. Does he say that it's filled yet?
I'll put the, while you look for that, I'll put the link out there.
Okay. Carla wanted to join. She posted that at 12:53, so a little while ago. And he has not said that it's filled yet. So I think we're good, pretty good yet for a while.
Okay, there's the link if you guys want to take a look if you're interested in going out tonight. I don't know about the weather forecast tonight. It looks like they might have some clouds, but it may not be totally clouded out. So you might want to take a look at that.
Okay.
All right. If there's nothing else. All right, everybody. Thank you guys for coming. I hope to see some of you next week and be safe in this COVID time, and we'll talk to you soon. Thank you guys for coming.
Have a good one.
Bye. Bye. Thanks, Steve.